Welcome to Brain Vision.
For this example, we have a pretty interesting question here. Given that we have some ideal neon gas in this cubical container, we want to know what the average rate of collisions is with one wall of the container. So we're given all these parameters here, like the length of a side of our cube, the number of moles, the temperature that the gas is at, and the mass of a single neon atom. So let's break down what rate of collisions is going to mean. We'll call it R. So R is the rate of collisions with one wall specifically. So we know that this is going to be a number of collisions per time, since it's a rate per time. So if we can break down how many collisions happen in some time interval that we decide upon, then we can probably get a pretty good estimate for the rate of collisions here. So the specific time interval we're actually going to look at is the time it takes for a single neon atom to hit one wall, say this wall, travel all the way to the other wall, collide with that wall, and then come all the way back. And the reason we're going to look at that time interval is because we know that within that time interval, there has to be at least one collision with our wall here, right? You can imagine if our atom started just barely away from this wall, like here's a side view. Maybe at the start of our time, right, our atom was just about to collide with this wall. And then it makes its collision, right? It travels all the way to this other wall and then all the way back to this wall and hits it again. So you can see that in the time it takes to travel back and forth, we will have had only one collision. So it's guaranteed that we need to have at least one collision within the time it takes to travel a distance 2L. Okay, so we're interested in the time it takes to travel 2L. Well, if we want to figure that out, we're going to need some sort of velocity, right? If you remember from mechanics, velocity is the distance over time. So if we have the velocity and we have the distance, we can figure out the time it takes to travel that distance. And the velocity we're actually going to use to figure this out is the RMS speed. Because the RMS speed is what determines the speed at which molecules will drift through this container, right? And if you remember, the VRMS is equal to 3 times kBt over the mass of an individual atom or molecule that we're dealing with. So our time interval t, if we solve this equation for t, is just going to be the distance over the velocity, where our distance is going to be 2L, right? Because we want to know how long it takes to travel 2L. And our velocity is just going to be VRMS. All right. So now we're getting somewhere. So if we look back at our equation for the rate here, number of collisions per time, well, we have an expression for a time interval now here, right? This is the time for guaranteed that one collision will occur? Well, if that's the case, then our number of collisions is just one collision, right? So R would be equal to one collision in a time interval of 2L over VRMS. Or if we flip that over, we'll have that R is equal to VRMS divided by 2L. And this is for a single molecule just bouncing back and forth in this direction, right? So you'd think that if this was for a single molecule, then the way we get the same equation for n molecules is we just multiply this by n. And we're almost right. But in reality, when we think of our box here, we're going to have molecules traveling in all sorts of directions, right? We're going to have some traveling this way, some traveling this way, some traveling this way. So they'll be going all over the place. So we can imagine that for a large number of molecules, we can approximate that about 1/3 of them will be making collisions in the x direction, about 1/3 of them will be making collisions in the y, and about the other third will be in the z. So really what we want to do is take this equation for the rate of collisions for n molecules and divide it by 3, since we have 3 axes here in our 3D space. So this is going to be our final equation for the rate. So now all we have to do is just plug in all of our values. So we still have to calculate the RMS and the total number of molecules. Since we don't have big N, we have little n, the total number of moles. So let's go ahead and do that. So if we plug in all of our numbers for VRMS, remember VRMS is the square root of 3 kBt over the mass of neon in this case. We're going to get 601.96 meters per second. And then we also wanted to find the total number of molecules. And remember, we can relate the total number of molecules to the moles of a substance with this equation. The number of molecules over Avogadro's number is equal to the number of moles. Or if we multiply both sides by Avogadro's number, we'll have Avogadro's number times the number of moles gives us big N. And since we have 1 mole of gas, we just have Avogadro's number worth of atoms, which is 6.023 times 10 to the 23rd atoms. All right, so now we have everything we need to plug into our equation here. And if we do that, our approximate rate of collisions with one wall of the container is going to be 2.01 times 10 to the 26th collisions per second. So there you have it. We just determined the rate of collisions per second with a single wall of the container, given that we have 1 mole of gas, of ideal neon gas, that is at 293 degrees Kelvin, where the volume that they're colliding in is a cube with side length 0.3 meters.